lab today, we are going to be looking at oscillations and what they look like in a lab setting when they are applied to a spring object. So what is this lab about? We are going to analyze the video of an object taken from a spring and let to oscillate in 2 dimensions. We are going to analyze this in Tracker and take the data that we find of its position and time. Then we are going to input that into GlowScript, and we're going to create a computational model in GlowScript to understand how oscillations work from a spring and mass. The physics principles that are involved in this lab include energy principle, forces, and then the velocity and position update. So the energy that is involved is the idea that energy is equal to kinetic energy plus potential energy, when kinetic energy is 1/2 mv squared. And to be able to better understand the spring potential energy, we have to look at L naught as the relaxed length, L as the position of the spring, and S as the magnitude of L minus L naught. So then the forces that are involved is spring force, and then gravitational force, F equals ma, or mg in this case. Net force as spring force plus force of gravity. We can follow this video along in Tracker, where we take these objects and it is suspended. Tracker records the data and creates a plot like the one on the top right. And then this follows a line of code to calculate out what this would look like over the same time step. So on the left, we have the position versus time graph, which includes in blue the model position versus time, and red the observed position versus time that we just saw in the prior video. As you can see, they're pretty similar in length, although red goes a bit lower than the blue one does. On the right, we see the graph of the change in energy, where blue is kinetic energy, red is gravitational potential energy, green is spring potential energy, and yellow is total energy. These were calculated out and helped us find position versus time in the computational model, and we'll go into them in more depth. This is the video of what the computational model looks like as it is running, as it projects what the spring looks like in the video that we recently saw in real life. Let's understand the coding that we just went through to come up with that computational model. We first start at the top left by setting the ball mass as 0.402 and the ball position. The ball mass was found from the edX videos, and the ball position was found from a Tracker video. Then, as we go down, we set the gravitational constant as 9.8, the spring constant, which we calculated from the videos, the relaxed length of the string, which we also calculated from the videos. Then we go into calculating L, L hat, and S, and we are able to follow these equations to do so. Then we compute the initial kinetic energy, gravitational potential energy, and spring potential energy, and total energy, based on the equations that we previously went over. Then we enter the while loop. This loop is what happens when we go from time equals 0 to 9.07 seconds, which is the length of our video. And we take into effect, we set force gravity, we calculate force spring, and then net force. Then with that, we're able to calculate the velocity and then the updated position. After we've done that, we can update the spring and find the new L, L hat, and S for this time step. We're able to do this by taking into account the kinetic energy equations that we went in before, and then updating them to find delta K. And then we were able to do this for gravitational potential energy, spring potential energy, and total energy. Now that we have come up with these delta K, delta UG, and delta US values, they are put into the graph that we saw previously. So what does this all mean? Is the energy principle satisfied? Yes, it is. As we see in this graph, the total potential energy, or the total energy, is in yellow, and it is constant at 0 for the entire time. Even though the kinetic and potential energies fluctuate, as we can see, the kinetic and the spring force and the gravitational force all fluctuate and change, the total energy remains constant. And then what does this mean moving forward?
When we look at the graphs of the position data for X and Y, and we calculate the period of oscillation, we find that for X it's 1.614 seconds, and for Y it's 1.519 seconds, which is very similar. And this is because they were started from about the same positions, and due to energy, they moved about the same distance, so they stayed very similar.